Good afternoon, friends. Today again we are here at Sandhan for the mathematics lecture, and I am happy to tell you that today we are having one of the great professor of mathematics, Dr. Rajesh Thakkar, with us, and he is an expert in this today's topic, that is operation research. He is going to deliver us 4 lectures on this operation research, and I hope that students will definitely enjoy his very sweet lectures. And let us see what he wants to tell. And we start with the first thing in the operation research, simplex method, which is the most basic thing in linear programming problem. So I request Professor Thakkar sir to deliver his wonderful lecture.
Thank you. Hello, and how are you? Dear friends, have you ever thought what is the process we have to do most of the times nowadays? We have been doing our daily routine, but then one thing which we always need to do is decision making. Whether it's a small thing or a big thing, we have to go for decision making. ઘણી નાની નાની વસ્તુઓ માટે પણ આપણે નિર્ણયો લેવા પડતા હોય છે. પછી એ ટૂથબ્રશ ખરીદવાની વાત હોય કે કાર ખરીદવાની વાર હોય. પહેલાંના સમય કરતાં અત્યારે ડિસિઝન મેકિંગ વધારે ડિફિકલ્ટ બન્યું છે. પહેલાં ઘણી લિમિટેડ પ્રોડક્ટ્સ હતી, ઘણી લિમિટેડ બ્રાન્ડ્સ હતી, ઘણા લિમિટેડ રિસોર્સિસ હતા. હવે પરિસ્થિતિ બદલાઈ ગઈ છે. હવે એક કાર ખરીદવી હોય તો આપણી પાસે ઓછામાં ઓછા 20 સારા ઓપ્શન્સ છે. So decision making is becoming more and more difficult nowadays. But don't worry, mathematics is there for your help. As you might be knowing, operation research is one of the branches of mathematics which is dealing with a great variety of applications. લોકો એમ કહેતા હોય છે કે મેથેમેટિક્સ વધારે પડતું થિયરેટિકલ છે. ખરેખર મેથેમેટિક્સ ખૂબ ઉપયોગી છે. એ જાણવા માટે ઓપરેશન રિસર્ચ ખૂબ સારો વિષય છે. ઓપરેશન રિસર્ચમાં આપણે ઘણી વસ્તુઓ જોઈએ છીએ. સૌથી વધારે વપરાતો શબ્દ ઓપરેશન રિસર્ચમાં છે લિનિયર પ્રોગ્રામિંગ પ્રોબ્લેમ્સ. આપણે ઘણી બધી વસ્તુઓ અને સ્થિતિઓને લિનિયર પ્રોગ્રામિંગ પ્રોબ્લેમ્સમાં કન્વર્ટ કરી શકતા હોઈએ છીએ, અને એના આધારે આપણી પાસે ઘણા સારા ઉકેલ મળતા હોય છે. કોઈ પણ એક લિનિયર પ્રોગ્રામિંગ પ્રોબ્લેમ આપણી પાસે આવે પછી એના ઉકેલ માટેની રીત આપણે વિચારવી પડે. જે રીત સૌથી વધારે વપરાય છે, સૌથી વધારે પોપ્યુલર છે, એનું નામ છે સિમ્પ્લેક્સ મેથડ. સો ટુડેઝ અવર ટોપિક ઇઝ મૂવિંગ અરાઉન્ડ સિમ્પ્લેક્સ મેથડ. We'll see a small presentation on simplex method. The first thing is, what's the simplex method? Simplex method is the classic method for solving LP problems. Many of the LP problems are solved very effectively by simplex method. It was invented by George Danzig, who was a member of Stanford University, and this was invented in 1947. It's a very pleasure that the journal Computing in Science and Engineering listed the simplex algorithm as one of the top 10 algorithms of the 20th century. You can simply realize the significance of this method. You might be knowing that the name of the algorithm is derived from the concept of a geometrical concept named simplex, and this name was suggested by a mathematician called T.S. Moskine. Let us see, when we say it's a simplex method, what do we mean by simplex? Simplex is a word from geometry, and in geometry, simplex, whose plural is simplices or simplexes, is in fact a generalization of the notion of a triangle or tetrahedron to arbitrary dimension. If we look at it specifically, an n-simplex is an n-dimensional polytope, which is the convex hull of its n plus 1 vertices. Very popularly, if you look at a 2-simplex, then it's a triangle. So we have to see that if it is an n-dimensional figure, then vertices must be n plus 1. So if you look for 2-simplex, it's a 2-dimensional figure, but it must have 3 vertices, one more than the dimension. So it's a triangle. If you go to a 3-simplex, it's a 3-dimensional figure with 4 vertices. We call it tetrahedron, and so on. The question is, why do we call this method a simplex method when there is no geometry seems to appear in the method? So simplices are not actually used in the method, but one interpretation of it is that it operates on simplicial cons. So when you go in the description of our constraints, we might get simplicial cons, and so perhaps so the method's name is given simplex method. So now we'll see an example of a simplex method. As we know, a simplex method is used to solve linear programming problems. Simplex method has many versions. We'll go with the simplest version of a simplex method in this way. So we go to the first example, which is a minimization method. In fact, there are two algorithms, one for minimization and other for maximization. We'll go for minimization method. We can look at the screen. The problem is maximize z equal to 4x1 plus 3x2. This is said to be an objective function in LPP. Then we have four constraints. The first constraint is 2x1 plus x2 less than or equal to 1000. The second is x1 plus x2 less than or equal to 800. Third is x1 less than or equal to 800, 400 it is. And the last is x2 less than or equal to 700. The last non-negativity condition is, which is always there, x1 and x2 must be greater than or equal to 0. So this is the problem given to us. As we know, before we start solving this problem, we have to go for something called a canonical system. So we next go to canonical system. We'll see how can we construct a canonical system. So the canonical system has first step. Our LPP has to be converted into minimization. So if it is in maximization, we have to convert it into minimization. So that is what we are going to do first. So if we apply this process, our function, objective function now changes to minimized. It is minimize minus z equal to minus 4x1 minus 3x2. So it's a very simple process. If you have a problem of maximization and if you want to convert it into minimization, you simply have to join minus to all coefficients. So our objective function is converted into minimization. Next, we are having constraints. Okay, so we are changing our constraints which are in inequalities, we'll be changing them to equations. So we'll next see the constraints. Okay, these are the constraints. You might have observed that earlier we had less than or equal to, but now it has become equal to. This is why it is becoming so. We are adding some extra variables so that left side rises up and it becomes equal to right side. So we are adding four different quantities. We call them variables x3, x4, x5 and x6. So our inequalities have converted into equations. And of course, these three extra guests must be non-negative. So if you go to our non-negativity conditions, it has enlarged. Earlier it was only x1 and x2 must be non-negative. Now it is x1, x2, x3, x4, x5 and x6 all must be non-negative. So this is what we call a canonical system. So we have converted our system, our problem actually, into something called canonical system, which is lying rather beautifully because we don't have any inequalities. We have equations everywhere in the constraints and our objective function has turned into minimization. The data which we just had is written on the table form now. So the first table actually reflects the data which we were looking at the screen little earlier. Yeah, so this is the data which is converted into table now. We can see the table here. The table has the first two columns. The first column is basis. If you look at the first column, there are four variables x3, x4, x5, x6. You know, they are the guessed variables. Actually, they were not in the system, but we have introduced them. Since they were introduced in the inequalities of the less than or equal to type, we call them slack variables. So they are the guessed variables, as I said, and you know, in India we honor guests a lot. So we honor our variables by putting them into the basis. Right second column is called x, which is actually the variable right side of the constraints. We can see they are 1000, 800, 400 and 700. And if you accommodate right side of the constraints, naturally left side will feel hurt about it. So let us take care of left side as well. So the rows, actually the first row, if you look at that, 2, 1, 1 and 000, they are reflecting the first row of our constraints. Similarly, we have 4 rows. And what about the last row? Last row, in fact, gives the values of the objective function. If you recall, our objective function's coefficients were -4 and -3 with x1 and x2. Since there were no x3, x4, x5, x6 in the objective function, that last row contains many zeros. So this is the first table. You just observe these values very well and try to remember these values. Now we'll see that the same table appears on the board. So this is the table which you were just looking in the screen. In fact, this gives the initial basic feasible solutions for the LPP. So we can see that there is no x1, x2 over here. So the solution suggested by this table is that since x1 doesn't appear here, in fact this is said to be the solution region. Okay, and since there is no x1, x2 appearing in the solution region, we say that x1's value is 0 and x2's value is 0. This is said to be the initial basic feasible solution. But naturally x1 equal to 0 and x2 equal to 0 is never a solution. So we would love to improve our solution. So in fact this process is an iterative kind of a process. So we will be moving towards better solutions, and that is what we should do in life as well. If we don't have good solutions, we should go to better solutions. So this first solution is naturally not logical to us. We would never appreciate such solutions. The question is how to go to a better solution from this non-appealing solution. We have a little process to do that. We will be applying something called elementary row operations. Let us see what we can do here. First of all, we look at the coefficients of the last row. Okay, here we can see that in the last row we have two negative numbers, -4, -3, and then all zeros. The question is that this solution is not the best solution that is reflected in the last row. If last row has any negative number, that simply suggests that this solution is not the best one. So our task starts now. We would love to go to a better solution. Once again, we would love to see on the screen our presentation, that is table number 1. In the last row, we can see that there are two negative numbers, -4 and -3. We can see that -4 is the most negative. So we will select with that column which has -4. So that column, which is actually a column of variable x1, that is selected, since it has the most negative number, and we never would like to have negative numbers at the end. So that column is selected. As soon as that column is selected, then we find something called ratios. If you can look at the last column. Okay, since we selected x1 column, our ratios will be x divided by x1. So second and third column, if you observe, we go for it. The first ratio will be 1000 divided by 2, that is 500, appearing in the last column. So 1000 divided by 2 is 500. If you go to the next, 800 divided by 1, that is 800, then 400 divided by 1, that is 400, and finally 700 divided by 0, that is not going to be a positive number, so we do not bother about it. We are just interested in the positive ratios. There are 3 ratios, luckily all of them are positive. We would love to find the smallest positive ratio. We can see that the smallest positive ratio is 400, so we will select that row. So first we selected a column, we will call it a bad column because it is having a negative number which we would not like to have. Then we selected a row. We can see that there is one element which is an intersection of that bad column and bad row. Yeah, that is it, it is 1. We call it a key element, or many a times we call it a leading element. So once we selected a column and a row, we will get a leading element. Now the question is, this table 1 will be changed to table 2, and the question is how to do that. Once again we come to the board and we will see how this process is done. So as we could see in the slides, this column was selected first, okay. Then we had ratios, and after selecting the ratios we selected the minimum positive ratio. that ratio was 400. So, that row was selected. Okay. So, this process is what we have done so far. Now, we will start with this special row. As we know, this 1 is the key element or leading element. Okay. Now, we start with this row which we selected, we will divide the whole row by the key element. If we do that, then our table 2 will start. So, we will make table 2 here. Table 2 will have a similar format what we had in table 1. First of all, we will start with bases. The first change in table 2 will come in bases. This variable x5 is replaced by that variable x1. Okay. So, the basis will become x3 is unchanged, x4 unchanged, but now this x5 is replaced by x1 and x6 is as it is. Okay. Next we have capital X or capital XB, and of course, 6 variables x1, x2, x3, x4, x5 and x6. We will make this table and we will see that this table gives a better solution. Okay. First of all, when we start filling this table, we will start with the selected row. This selected row of the table 1 will be divided by this key element. Luckily, key element is a wonderful element 1. So, if we divide by that, we are not affected. So, the row will be as it is. So, x5 which is now x1, that row will be as it is. So, that is 400, then 1, 3 zeros and 1 0. So, that row is filled. So, at least a bit of work is done, that special selected row is filled in. We go to the specially selected column. We can see that it was x1 column in table 1. Once again, this is a nice column. We will fill it by very simple numbers